Good afternoon. How you doing, class? Hi, Cole. Hi, Christina, Jasmine, Alexis, Cam. It's good to see you. Well, it's good to see your comments. We'll give people a minute to join us here. All right, so we were. I will give people a minute before we start, but we were. Last time we spent time talking about what your next practical exam will be like, and I outlined that for you. So I'm putting the finishing touches on the assignment associated with that practical, and just like last time, I'll post it up with the data for you to practice as much as you want before the day of the practical, and then you do the practical, close notes, close books, no resources, just your brain and a brand new instance of a ArcGIS Pro project. Well, I'm actually going to supply you with the project file to get started with. A brand new, fresh copy of that project package to get started. So yeah, you practice. So we were talking a lot about that, and so one of the things I ended. What did I end with? Oh, the thing I ended with was showing you that oftentimes, well, maybe not oftentimes, sometimes you'll find yourself in a situation where your features, this won't happen with point features unless you have, it could happen just in sheer scale of the number of features that you have in a layer. But when it comes to individual features, if you have a line feature or a polygon feature, one feature could be hundreds, thousands, even millions of vertices and line segments connected together to create the geometry of that feature. So when you try to apply a tool, a geoprocessing tool to that feature, it might choke. It may not be able to complete that task in a reasonable amount of time. What's a reasonable amount of time? Well, it depends on what your constraints are, what your time budget is, but for the practical exam, anything that takes more than a few minutes to process is not a reasonable amount of time, because you only have 2 hours to complete the whole thing. So what I was showing you was, I got it open here. Let me get set up. There we go. And so I was showing you this. So this is one of the features in my my feature layer that contains all of the locations, polygons for locations that are administered by the National Park Service. And this particular location is Lake Roosevelt National Recreation area. It is in, looks like Washington state. And so the pink polygon here is the original feature. And if you remember, what I did was I applied the simplification tool to this feature when I selected it, and the result of that simplification tool was this black polygon, this polygon which is represented by the black outline here. So when you zoom out, you don't see much difference between the two. The black outline polygon encapsulates, let's call it the macro features of this park, of this recreation area. But when you zoom in, you see that on the micro level, there's deviation. But if you zoom in a lot, you'll see there is a lot of vertices and line segments that are creating this border of Lake Roosevelt Recreation Area in the original feature. And I've simplified it a great deal. Okay, so now if you remember, I tried to use the buffer tool on the I tried to use the buffer tool on this Lake Roosevelt recreation area in its native state before I simplified, and was just running. And it I don't know how long it would take to finish, if it ever would. I mean, I got a pretty capable computer here to crunch away on this problem, but you know, it might never finish before my computer runs out of resources. So, but anyways, I don't know how long it would take. I stopped it before it finished. So let's use the buffer tool on my simplified polygon and see if this is much better. Tools. Okay, so we'll use the buffer tool, and my input feature is the simplified polygon. Make the output feature class, what's it going to call it? Simplified polygon. I'll call it buffered. And let's do a distance of 50 miles for my buffer. We'll include the polygon that's being buffered itself in the result. I'm going to do geodesic, shape preserving buffering, and no dissolve. Okay. And so here we go. Just working. Done. So that finished. I wasn't counting, but that was like maybe 5 seconds to complete that operation. And now I have this new feature, which is Roosevelt Recreation Area buffered out to 50 miles. Okay. Creating a 50-mile buffer around that zone. All right, so that's enough of that for now. Guess I'll save this project. And but now let's continue with chapter material that's from chapter 8 in your textbook. And so in chapter 8, it deals with the analysis of spatial patterns, finding, and the type of data that's being used in chapter 8 is data that's related to crime incident reports in a city, maybe Philadelphia. We'll see in a minute. So we'll look at some tools that allow you to summarize spatial patterns. And you think, well, what would be like a feature of a spatial pattern? Well, if you have a bunch of dots, the opposite of pattern is completely random. So if you have a feature class that is showing, the data we'll be looking at are robbery data for the city, and if robbery locations, remember it's spatial data, if robbery locations are completely random, there won't be any clusters in this data. They'll just be dots, and every dot will just be randomly spaced out from every other dot. Do you think that's going to be the case when it comes to crime data? Probably not. And so you can, if you're like law enforcement, how much you use this type of analysis. Well, one thing that comes to mind is if you can find clusters, places where a certain type of crime is more prevalent, you can use that information to assign resources to that location, crime prevention, police resources to that location. Another thing, and I think we'll look at this a little bit too, is I wonder if different types of crimes have the same types of spatial patterns. Do like robberies have the same spatial distribution as, I don't know, vandalism, other types of property crime. So we'll take a look at that. Excuse me. All right. And then the other thing that you can do is not only can you look for spatial patterns, you can look for temporal patterns. And so spatial patterns denote patterns in space. Temporal patterns denote patterns in time. And when we think about temporal patterns, the kind of pattern that you probably are most familiar with is a trend. And you probably have done this, where you plot some variable as a function of time, and you see that over time that thing is increasing, that thing is decreasing. If you have no temporal pattern, what you see is when you plot that variable over time, you just have a flat line. So the absence of spatial patterns are randomness in space. Something is equally likely to occur at any point in space. The hallmark of temporal, or the absence of temporal patterns over time, is that whatever you're studying is the same at every point in time. Okay, so it gets even better. Okay, because there's tools in ArcGIS Pro that not only allow you to look at spatial patterns and temporal patterns, but to look at spatial and temporal patterns simultaneously. And you can make something called a space-time cube. It just sounds like sci-fi when I say it. Sorry. Space-time cube sounds like Star Trek. But it's a real thing. And it's pretty neat to look at it, data summarized in both a spatial way and a temporal way. And it's sorry, I just can't help space-time cube. And one of the things that you need in order to make these tools useful are you need really big data sets. You can't generate a space-time cube from like 5 data points. You need a lot more than that. So we'll look at that too. And I'll do my best not to screw up the tools as we go through it. They're somewhat complicated. I find them somewhat complicated, and actually interpreting the results, on a sort of a superficial level, it makes sense to me. But on a more in-depth, deep level, it's sort of like it's sort of like magic. The mathematical tools that are used to derive the numbers, the colors, the values that you get, are hidden from us, and that's dangerous. That's really dangerous, because when you guys get to my capstone course, you'll be expected to do a data analysis, to do some statistics, and we'll learn enough in that course to make you dangerous when it comes to being able to do statistics and to understand what is the appropriate tests to do in different situations. But there's what you find is that whenever you're doing some sort of mathematical analysis, and these are all based on statistics. These tools that I'm going to show you today are based on statistics. There's underlying assumptions, and like, for example, maybe there's an assumption of normality. The data is normally distributed in space, and that may or may not be true. But oftentimes we're not even aware of these assumptions, and we just use the tool. We show the results, and it's fancy and neat and flashy, so it can be impactful even if it's not very meaningful. All right. You guys still out there? My stream isn't. Oh, there, you're back. Never mind. All right, let's go back to the desktop and get started on this. So I need to go to the right place. It's in here somewhere. Crime incidents. Here it is. This is the project we're going to work with. All right. Let's see. All right, so we got a geodatabase with a crime feature class. It's on our map. Let's look at the attribute table. Yeah, this is Philadelphia. Well, hold on. It looks like, yeah, there's New Jersey, there's Pennsylvania. Here's where I grew up, over here in Lancaster County. So let's take a look at the attribute table. Oh, I already have it open. All right, so there are 74,011 data points, 74,011 rows in this layer, in this attribute table associated with this layer. We're dealing with a point feature class. All right, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 fields in our attribute table. Sector, DC, district, I don't know what that means. We have dispatch date, dispatch time, location block, crime code, and then the crime code is like police code. The crime column is, decoded for us every day. Language theft, thefts, burglary, make this bigger, non-residential, motor vehicle theft, burglary, non-residential. Here's robbery with a firearm, robbery no firearm. So we have spatial data, but it's also temporal data, because we have the time that I'm guessing the dispatch time, dispatch date and time are the date of occurrence. I guess that doesn't necessarily have to be the case, but it's whenever it was logged. So we have spatial, temporal, spatio-temporal data. That's a fancy way of saying it. Okay. So let's filter out some of the. Let's filter out most of the data. I think. Well, hold on a second. Let's look here. So let me sort ascending. So the very first data points are for January 1st, 2014, and it goes through December 31st, 2014. So we have 1 year. This represents 1 year of crime data for the city of Philadelphia. Whoa, that's a lot of crime. All right, so let's filter out the data for the month of January. And let's filter out just the robbery data. So it looks like there's 2 codings for robbery. There's robbery with firearms and robbery without firearms. So let's go to select. Let's do it this way. Select by attribute. From crime, let's do a new expression. And we want just the burglary stuff. So we want where the crime is equal to robbery firearm, or the crime is equal to robbery no firearm. So this will be all the robbery data. Doesn't matter if there's a firearm or no firearm. And we'll click apply. Okay, and then let's use the copy tool to create a new feature class out of this selection. Do copy. Oh no. Wrong tool. So the input feature, the output feature we'll call robbery. Robbery. Run. Okay, so I'll make the crime go away. So now I have less turned off the crime layer. You can see the robbery layer is a subset of the crime layer. All right, so let me clear all my selections. Here we go. And so now let's further refine this data set to just robberies. Turn off crime. Robberies in January. Okay, so let's do select by attribute again, and we're going to filter by dispatch date. So we want where the dispatch date is on or after. So this is, it knows that this is date. This is going to take too long to search the calendar. Did you see the calendar? It starts in 2020. So I'll just put it in my hand. So 1/1/2014. Can't tell if it's actually going in. 1/1/2014, and the dispatch date is on or before 1/31/2014. Okay, I think I got it right here. It's unfortunate I can't see it. Okay, 1 to 1:30, and I'll apply. Okay, and then I'm going to copy that to robbery January. I'll run it. Okay, so now robbery January is a subset of all the robbery. So what we have here, I turned off the crime in the robbery data, and what I have is this is all the robberies in the month of January for the city of Philadelphia. Okay, so I mean, you look at this, does it look random? Does it look like these are just randomly distributed crimes? I just thought of something. Let's talk about something here. So it's interesting. The crime data that we have here is it's positional crime. Does that make sense? Yeah, it's positional crime. It's a crime that's associated with a specific location. So think about this. These are robbery. You're robbing something, and that something has a physical location, like somebody's house, somebody's business, somebody's car, somebody's person. There's a physical location of where that event occurs. So they're positional events. We'll call them positional events. Is that true of all crime? Can you think of an example of a crime that's not positional? I want to wait and see what you say, because I was thinking about this recently. GIS is a powerful tool for analyzing data that has a spatial, positional attribute. Do you think of any crimes that aren't positional? In a geospatial sense, in a geographic sense, that you could assign a coordinate to. Is this too philosophical for a Wednesday afternoon? Too much deep thinking? Alexa's got something here. Let's see. some kind of online crime wouldn't be positional, like hacking or something. That's a good example. It's like, well, you could say, well, the server that was hacked had a location, but that's not really meaningful. Um, the it's not right. The internet is global. You could hack into a computer system if you have some um, connection via the internet to that computer system, and that connection could be anywhere. So there might be like a networking diagram showing the connections between bad players in the realm. Can you think of anything else that's not positional? Any other type of crime? I don't want to get myself into trouble, but I was thinking about this. A lot of the examples I was thinking were like the types of crime that we would call white collar crime, things like embezzlement and blackmail, um, and those sorts of things. Um, they're not really they're not positional in the same way as like a robbery or um, an assault would be. Um, so that's interesting because that means that those types of crimes aren't. They're not. You can't approach those types of crimes using the same tools that you would approach these same geospatial tools that you would use for these other positional crimes. Um, and and I was thinking, well, that doesn't necessarily mean that there's not a spatial reference that you could apply to those sorts of things. And but maybe in that case, the dimensions aren't latitude and longitude. There are other things and that define social stratification, like like income levels or levels in authority or I guess relationships to other people in power. There's other ways that you can stratify the world besides latitude and longitude. All right, that's enough digression for now. All right, back to the crime here. Okay, so what we're going to do is we're going to create something called a kernel density map. Let's see if I can find it here. There it is, kernel density. All right, so open this tool. It's in the toolbox up here. And so our input is going to be the robberies in January. Population field, none. So all these points are on equal footing. They're not weighted in that way. Output roster, let's call it robbery January density. So we're creating an image here. We're going to create an image. That's the output. It's creating a raster. It's not creating a vector data set. It's creating a raster data set. Output cell size. We'll keep the default here. These are calculated automatically for us. Area units. I think I'll keep the rest of the defaults here and just run it. And let's see what we get. Okay, so it's done. So it color coded in purple. I could change that to a different color scheme. Now let's keep it purple. I like purple. But if you zoom in here, what you see is click on one of these spots. Each pixel now in my raster. So here's a pixel. This pixel has a value of 15.37, and so think of that as the density of it's a number that corresponds to the density of robberies in that area, and it's assigned to class 5. So we got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes assigned to robbery frequency. And I guess, well, hold on, what was my units? Square miles. So the units here would be the number of incidents per square mile. So here in these high density areas, this is saying that there's the density of robberies at that point is 25 per square mile. So you do have these hotspots. Well, these clusters of where robberies occur, and you've quantified it. It's pretty cool. So let's make this a little bit transparent. That's too much. Here we go, 40%. And so you got a hotspot here. What's this? The neighborhood Stenton. And then there's a hotspot over here. I don't see a neighborhood name there. North of Kensington and west of Richmond. You got a hotspot down here. And looks like downtown Philadelphia. Got a hotspot out here. A cluster. I'm calling them hotspots. Clusters. I'm getting ahead of myself. That's cool. It's pretty cool. All right. So I'll close this tool, and but you can see that the result of this kernel analysis, this kernel. So it's called a kernel. Sorry. It's called kernel density analysis because the underlying mathematics of what's going on here is well, okay. I'm gonna again. This, even for me, this is almost like magic sometimes. I mean, I'm sure I could figure out the mathematics of what's going on behind the scenes, but the point is, when you click the tool in ArcGIS Pro, it just happens for you, and the assumptions, the formulas, the underlying conditions are completely obscured. They're just behind the veil. But what's going on here is it's building a model of the spatial distribution of the data. And so think of a kernel as sort of like a window that moves around. And the value at every pixel is a function of how many points fall in that window as it moves around. And so one type of kernel could be a Gaussian kernel, and it counts things that are close to that location more than it counts things that are further away when it's figuring out the frequency, the density of points in a certain area. All right. Okay, so let's keep going here. Got about 15 minutes here. So let's do something different here. Let's go back to the crime data, and I'll turn this off for now. And let's select a different type of crime, and just to compare. So let's see. We have some options here. What do you guys? Let me make this bigger. What do you guys want to study? Tell me in the comments. We looked at robberies. We've got aggravated assaults, burglaries, homicides, theft. I know what you're going to say already. What do you want to look at? I wonder what the difference is between burglary and robbery. What's the difference? I don't know. Do any of you know? Burglary. Does burglary have to do with a home? Does it have to do with like a building, a physical location? I say that because it's divided by residential and non-residential. So I'm thinking burglary is like robbing from a home. Huh. Do any of you know? All right. Let's do burglaries. So we got non-residential and residential burglaries. Okay. Jeez. There's a lot of them. Okay, and then let's get those to, here, I'll do it this way this time. Data export feature. So we'll export those to burglary. And actually, let's just keep going. So I have, let's see, my select by action. Shoot. Well, let's do this by steps. So we'll export this to burglary. Okay. And so burglary is a subset of crime, but it's a different subset from robbery. And then let's clear our selection and select by attribute again, and we're going to look for January again. Dispatch date is on or after 1-1-2014 to 2914, and dispatch date is on or before 1-31 2014. And I think I got that right. 1-31 and 1-1. Okay. Apply. Okay. And then we'll export that to a new feature called burglary January. All right, well, that's interesting. So maybe let's do a different symbol here for burglaries. Just change the color to, I don't know, nice purple. So I got burglary in January, robbery in January, and you know, it's hard to tell. Is there a I mean, you can definitely see clusters in the robbery data. Yeah, there's some clusters in the burglary data too. Are they the same? Well, let's find out. Let's try a kernel density on burglary. And we'll call this output raster burglary Jan density. And square miles, densities, planar, yep, okay. Same parameters as before. And let's use the same color ramp. Let's use a different color ramp. How about, yeah, we'll use red. And let's make it a little bit transparent. Okay, so turn off the points, and now we can compare. Now here's burglary data, And let me mess with the symbology of robbery too. Just kind of put things on. I don't want this gradient. I'm gonna just do. What I'm doing is I'm making a solid color scheme. Here we'll do blue. Reverse the ordering. And just making the lightest one no color. Alright. And, okay. So, burglary. Oh, I gotta flip that again. Hold on. Alright. So burglary in red, robbery in blue. Oh, that's cool. Look at this. Okay. So it's hard to show these at the same time. Maybe I'll change my base map here. Just change it to something more simple. Alright, and make the transparency even lower. I don't know, something like there, 16%. It's still hard to see through it. But you can see, so I guess I'll just, maybe I'll do this. Let's do swipe. There we go. Did you ever see this feature before? I have two active layers, and I click the swipe tool here, and if I click at the top and drag down, it makes the top layer disappear and the bottom layer show. Isn't that cool? So you can go back and forth and see the difference between the two layers. So this is the density analysis of burglary data, and then this is the density analysis of robbery. Anybody figure out what the difference is between burglary and robbery yet? I guess we can make the layers completely. Oh. Well, yeah, let's make them completely not transparent. Burglary is a property crime. Robbery is a violent crime against a person. Thank you, Kyle. Thank you. Now I know. So, burglary, there's some notable differences. There's similarities. Like, you know, here in this middle of the map, there's a high density of both types of crime. Let's see, what's the most notable difference? Well, here's a difference over here. Let's make these a little bit more transparent. So here we have a dense amount of burglaries, but not many robberies. So we're actually, in other words, there's a bright red spot here, but not a bright blue spot. Right here, just south of Belmont, on Ludlow Street. So that's, you know, that's knowledge discovery, people. We are, you know, this is, you know, knowledge discovery is like this idea that you can take large data sets and actually find meaning in them. And so we're discovering knowledge here. We found this spot in Philadelphia where there are a lot of burglaries, but not many robberies. And there's other places where there's a lot of both. So that's interesting. It's like, well, why? Then the question is why? Why are there a lot of property crimes there, but not a lot of crimes against people, robberies of people? Does it have to do with some socioeconomic factors? Does it have to do with something about the geography? Does it have to do with, uh, the presence or absence of police enforcement, or the practices, what they're doing? Maybe any building then, not just a home. Yeah, so burglary is, right, Cam, I'm including, it was divided into residential and non-residential, so I'm guessing burglary, residential is people's homes, and non-residential would be like businesses, or, yeah, what else is there? Offices, factories, stores. All right. Okay, so I think we'll call it a day there. Here, give me a second here. Let's see. Yeah, so on Friday, tomorrow in lab, we'll work through the next lesson. No, sorry, we're still on lesson six, and no, 5, 6. We're on lesson 6, and there's a few parts of that lesson remaining to complete. So that's what's on tap for tomorrow, and then on Friday we'll look at another type of analysis called hotspot analysis. All right. Let me see. Got any questions? I don't see any in the comments. So I'll see you tomorrow. All right. Have a good afternoon, everybody.